Welcome. Let your breathing slow and let your body settle into whatever is holding you tonight. There is nothing you need to do now but listen and let this story carry you gently downward. Marine snow falls without pause across every ocean on Earth. Right now, in every sea, pale flakes are sinking through darkness, falling as they have fallen since long before anyone stood on a shore. This is the story of that endless, steady fall. Sunlight reaches only the topmost skin of the sea. Below that thin layer, color fades toward blue. Then it fades to black. Almost the entire ocean lies beneath this narrow sunlit band, stretching down into permanent darkness. Nearly everything that ever falls through that darkness first began its life within this slender skin of light. Phytoplankton multiply by the trillions within a single sunlit afternoon. Each cell is smaller than a grain of salt, yet together they color entire stretches of ocean green. They need only warmth and light. Given enough of both, a single bloom can spread across hundreds of miles within days. These floating plants form the true beginning of nearly every story that follows them downward. A diatom builds its shell from dissolved silica before it dies. This shell forms in intricate glass-like patterns unique to each species. No two are quite alike. When the diatom dies, that fragile shell begins its long descent, carrying a trace of the sunlit world down into darkness. Billions of these small glass shells drift downward together, forming one of marine snow's most delicate threads. Copepods graze quietly through these floating meadows of algae. These small crustaceans drift among the phytoplankton, feeding almost constantly. They are barely visible. As they graze, they break apart clumps of algae, scattering fragments that will later sink. Their feeding, however small, already shapes what eventually falls toward the deep. Zooplankton release fecal pellets that begin the long descent. These small pellets are dense and rich in undigested nutrients. They sink quickly. Compared to looser debris, pellets like these fall with surprising speed, carrying carbon and nutrients away from the sunlit water above. In this way, even waste becomes part of the ocean's long downward exchange. Dead algae cells clump loosely into drifting strands. As phytoplankton die, their remains stick together in the water, forming pale, stringy masses. They hold together weakly. These loose strands drift and tumble, gathering more debris as they fall, growing heavier with every small addition. What began as a single cell joins, slowly, into something larger. Tiny animals cast mucus webs that trap passing debris. Some create sticky, nearly invisible nets, spun from their own bodies to catch drifting particles. These webs work like fine sieves. Whatever brushes against them, plankton, dust, fragments of shell, is drawn in and held together. Eventually, the web itself falls, carrying its catch down into darkness. Viruses burst phytoplankton cells, scattering their contents into the water. These viruses are far smaller than the cells they infect, yet astonishingly effective. Within hours, a single infected cell can rupture entirely. Its contents spill outward, releasing organic fragments that drift and clump with other debris. Even this hushed, invisible violence feeds the falling snow above. A biologist named Alice Aldridge first described these clumps in careful detail during the 1970s. Earlier nets had torn them apart. Working carefully underwater, she collected fragile aggregates intact, revealing structures far more complex than anyone expected. What seemed like random debris turned out to be intricate, living communities in miniature. Her careful work laid the foundation for decades of research that followed. Feel the next breath arrive on its own. Let it fill low, unhurried. Then let it go. Each exhale can stretch a little longer than the one before. No rhythm is required, none to keep track of. Shoulders can sink deeper into whatever holds them. With each breath, the body settles further into rest. Shed skins, scales, and molted shells also drift down amid the softer debris. Crustaceans cast off their outer shells as they grow, leaving hollow husks behind. Fish scales loosen and fall away over time. None of it sinks alone. Each fragment joins the slow current of decay, folding into the larger stream of falling matter, indistinguishable from everything else drifting past it. Marine snow earned its name for how closely it resembles falling flakes. Early observers, watching from submersibles, saw pale particles drifting downward through darkness. It looked exactly like snow, illuminated only by a submersible's lights. The flecks tumbled and swirled, the way snow catches a lantern's glow. The name simply described what anyone watching would have seen. Dust carried from distant deserts settles onto the ocean's surface. Winds lift fine particles from the Sahara and other arid regions, carrying them thousands of kilometers over open water. Land reaches the sea this way. Much of this dust falls onto open water, mixing into the surface layer. Sometimes it feeds the very plankton blooms that begin the falling snow. Volcanic ash sometimes drifts thousands of kilometers before it lands on water. An eruption can send fine particles high into the atmosphere, where winds scatter them across entire ocean basins. Some of it sinks straight down. Weeks later, that ash settles into the same slow fall as marine snow already in motion. A mountain on one continent can leave its trace on a seafloor, an ocean away. Grains of sand and flecks of clay mix invisibly into the falling mixture. Rivers carry these fine particles far out to sea, well beyond any visible coastline. Oh, wind adds its own share too. None of it stands out on its own. Bound together with organic debris, these mineral fragments become part of the same slow descent, indistinguishable from the softer material around them. A single flake can be a mosaic of 100 small endings. Within one loose cluster might lie a dead algae cell, a discarded shell, a scrap of mucus web, and fragments too small to name. Each arrived by its own path. Together they form something briefly whole. It will not last. Surface productivity feeds nearly everything living in darker water below. Nothing escapes this dependence. Fish, worms, and bacteria in the twilight and midnight zones all rely, however distantly, on what drifts down from that thin, sunlit layer above. Cut off the surface bloom, and the deep would eventually starve. The dark ocean survives on borrowed light, one flake at a time. Marine snow falls most densely where plankton blooms thickest, near coasts and polar seas. Nutrient-rich waters near continental shelves and cold polar currents support explosive growth at the surface. The pattern is simple. More surface life means more falling debris below. In these regions, the descent can feel almost like a true snowstorm, thick and constant. Open ocean deserts, by comparison, receive only the lightest dusting. A ship's crew once described the falling particles as the sea's own weather. Aboard a deep-sea research vessel, sailors watching remotely operated cameras noticed flecks tumbling past the lens for hours at a stretch. One officer likened it to snowfall from childhood winters. The comparison stuck. What began as an offhand remark became a phrase researchers still use today. Sunlight fades into deepening blue as the surface gives way to twilight. Above, the sea holds its familiar palette of green and turquoise, alive with light. Only a few hundred meters down, that brightness begins to thin and cool. Warmth fades first, then color follows close behind. Day and night start to blur into one hushed glow. This is where the long descent truly begins. Let your body grow heavy now, one part at a time. Feel your feet sink first, heavier than a moment ago. That weight climbs into your calves, then your knees, deepening with every breath. Your hips settle into the mattress, followed by your lower back. Shoulders loosen and drop. arms turn warm and still, hands resting exactly where they landed. Let your head grow heavy last, cheek easing into the pillow. Twilight zone waters begin near 200 meters down. Below this line, sunlight thins into only a faint suggestion of daylight. Photosynthesis becomes impossible here. Plants vanish completely, along with the last hints of green. Snow continues falling regardless, steady through this dim, filtered world. Creatures below have adapted to a permanent state of dusk. Color disappears gradually, red vanishing first, then orange, then yellow. Water absorbs each wavelength at its own depth, filtering the spectrum like a fading rainbow in reverse. By around 30 meters, red has already vanished from view. Orange and yellow follow soon after, swallowed by the deepening blue. Only blue light lingers long enough to reach these depths. Everything else is memory by then. Falling flakes descend at their own unhurried pace. No two travel at quite the same speed or along quite the same path. Some tumble in gentle spirals, others drop almost straight down. Currents nudge them sideways for hours before releasing their hold. Nothing here is rushed. Each flake simply follows gravity, density, and time. Larger aggregates can sink hundreds of meters within a single day. Weighted by denser material, like fecal pellets or clumped shells, bigger clusters fall quickly compared to finer, looser ones. A dense flake released near the surface at dawn might reach the twilight zone by nightfall. Size and density decide the speed. The heaviest travelers rarely linger in any single layer for long. Smaller flakes may take weeks to complete their descent. Loosely bound and nearly weightless, these fragments barely outpace the water itself. Faint currents can carry them sideways for miles before they ever settle. Some never arrive at all. Others simply wander between layers, suspended in no particular hurry. Bacteria settle onto each flake, building miniature floating colonies. The colony forms fast. Within hours, a flake becomes host to countless microscopic passengers, feeding on its organic material as they multiply. Their activity helps bind loose particles more tightly together. A flake, in this sense, functions as a tiny floating ecosystem, complete and self-sustaining for as long as it lasts. Thousands of bacteria can crowd within the folds of one small flake. Each fold offers shelter, a hidden pocket for growth. Under a microscope, what looks like a simple speck reveals itself as a living tapestry. Some bacteria break down proteins, others target fats or sugars, each claiming a niche within the same tiny structure. Together, they turn one falling scrap into a busy, temporary neighborhood. Marine biologist Mary Silver spent years cataloging how these aggregates form and break apart. The work took years, using specially designed cameras and collection traps lowered from research vessels. She tracked flakes as they formed, dissolved, and reformed again and again. Her record showed marine snow was far from permanent, constantly shifting shape throughout its fall. Silver's documentation helped establish marine snow as a serious subject of oceanographic study, not merely a passing curiosity. Small submersibles sometimes catch sight of larger clusters, known as snow flurries. These form when many small flakes merge into loose, cottony masses. Caught in a submersible's lights, they appear pale and slow-moving, tumbling through the beam. A pilot watching one pass might mistake it for an actual snowstorm. The illusion never lasts. It is only the sea's ordinary fall, made visible for a moment. Each night, across every ocean, small animals rise toward the surface in a great vertical migration. Krill, copepods, and tiny fish ascend together, following the fading light. Their combined movement forms the largest migration on Earth, though almost no one above ever sees it. By dawn, they retreat downward again, back into deeper water. The rhythm repeats without fail. Somewhere beyond hearing, A low hum rises and fades, like a ship's engine felt through a hull far away. It arrives without hurry, holds a moment, then eases back into stillness. You do not need to name its source. Let your shoulders settle further into the mattress. Each breath can stretch a little longer than the last, each exhale looser than the one before. There is only this room, this breath, this steady return of sound and silence, asking nothing of you. Fish and krill feed eagerly on falling snow throughout this nightly climb. As they rise through darker water, they intercept flakes that might otherwise have taken weeks to descend further. Some snap up loose aggregates whole, others sift through clouds of finer particles. This feeding briefly redirects material meant for the depths into other bodies. Nothing is wasted for long. By morning, many of these same migrators descend again, carrying part of what they ate down inside their own bodies. Their waste and remains sink far faster than any loose flake could manage alone. In this way, animals act as a shortcut through the water column. Hours can replace weeks. What began as a day's meal near the surface may reach great depth before the night is over. The mesopelagic zone, that dim twilight layer, holds more fish by weight than nearly any other part of the ocean. Much of this life avoids nets, lights, and cameras alike, staying just out of reach. Early sonar surveys once mistook dense schools of these fish for a false ocean floor. Estimates suggest their combined weight may exceed that of every other fish population on Earth. Most swim untouched, unnamed, and largely unseen. Falling particles pull carbon downward with them, carrying it out of easy reach of the atmosphere above. Every flake of marine snow contains carbon drawn originally from air near the surface. Once buried in deep water or seafloor mud, that carbon can stay locked away for a very long time. This transfer needs no machinery. It happens flake by flake, endlessly, as part of the ocean's steady rhythm. Scientists call this quiet process the ocean's biological carbon pump. The name sounds mechanical, though nothing about it moves with urgency. Trillions of tiny organisms, each living and dying on its own schedule, keep the pump running without a single moving part. Together, their falling remains shift carbon from the sunlit surface into the deep sea's long-term storage. It runs without design. It rarely stops. Most falling carbon never reaches the ocean floor. Bacteria, small animals, and simple chemical breakdown intercept the majority on the way down, releasing it back into the water as dissolved gas. Not all of it escapes. A smaller portion survives the full descent to settle in sediment. Spread across the whole ocean, even that portion adds up to a steady, enormous transfer. A sediment trap, moored in open water for a full year, once revealed just how much falls unseen. Researchers lowered the funnel-shaped device to a fixed depth, then left it collecting through every season without pause. It never stopped. When they finally hauled it back, the material inside told a story of steady, continuous fall, spanning every month in between. Its findings confirmed what had only been suspected before. Broken flakes can slowly reform, particles finding one another again, the way fog gathers itself out of open air. A collision, a swirl of current, or a single strand of mucus is often enough to pull separated pieces close. What breaks apart under turbulence rarely stays broken for long. The pieces simply meet again. Reformed clusters continue their fall as new, slightly different flakes, carrying pieces of more than one earlier one. Amphipods and other small crustaceans sometimes ride along on sinking clusters instead of swimming their own way down. Clinging to the surface of a flake, they feed on its softer material as it falls. The ride costs them almost no energy. It offers food and transport at once. For a small creature in open water, that combination can mean the difference between an easy descent and an exhausting one. Lanternfish climb toward the surface almost every night. following the same falling supply upward instead of down. Rows of light-producing organs line their bellies, faint beacons in the dark water. Beating heavily through the night hours, they retreat to deeper water again before dawn light returns. Their bodies, like so many others, are built on a steady diet of sinking remains. Let warmth settle first into your hands, loosening each finger one by one. From there, it moves into your wrists, then up through your arms, filling the space behind your elbows. Let it reach your shoulders next, and feel them drop a little further from your ears. Warmth spreads into your chest, slow and even, rising and falling with each breath. Let it pool finally in your face, easing your jaw, softening your brow, until your whole body rests, warm and heavy, sinking gently into the mattress below. Sperm whales diving into deep water to hunt squid depend, without knowing it, on generations of falling snow. Squid feed on smaller creatures that were themselves nourished by sinking particles far above. By the time a whale finds its meal, that chain may stretch back through many small lives and many years of quiet fall. The whale simply surfaces again, unaware of how far its food has traveled to reach it. By 400 meters down, sunlight has almost entirely disappeared. What remains is a faint, deep blue glow, thin and colorless. Fish and other creatures at this depth see only shadows and outlines, if they see at all. This marks the last real threshold of daylight, the edge where the ocean's twilight finally gives way to true dusk. Below 1,000 meters, darkness becomes complete and permanent. No trace of sunlight has ever reached this deep, not once in the entire history of the ocean. Here begins the region divers call the midnight zone. Whatever light exists below this line comes only from the creatures themselves. Pressure at these depths would overwhelm any unprotected human body within moments. Water pressing down from above builds steadily with every additional meter of depth. By the deep seafloor, that weight reaches levels no human tissue could withstand unaided. Submersibles built to survive it wear hulls of thick titanium, shaped like spheres to spread the crushing force evenly across their surface. Creatures at this depth often wait patiently for whatever finally arrives from above. Many have slowed their own metabolism to nearly a standstill, conserving energy across long stretches without food. Stillness itself becomes a kind of strategy. A single falling flake, arriving after weeks in open water, might be the only meal some of these animals see for a very long while. Pilots aboard the submersible Alvin captured some of the first clear footage of falling marine snow. Diving through open water on early research missions, their floodlights caught particles suspended and sinking in real motion, something sediment traps alone could never show. What scientists had inferred from samples pulled up from below, these pilots finally watched happen with their own eyes, flake by flake, through a small round window of glass. Anglerfish, tripod fish, and other slow-moving forms rely on the falling supply. They rarely chase their food. Instead, each waits for the current to carry a meal within reach, sometimes for days at a stretch. A tripod fish props itself above the seafloor on three long fin rays, like a small stilted platform. From there, it watches the water above for anything drifting down worth catching. By the time a flake reaches this depth, it has often lost most of its original mass to hungry mouths above. Little remains of what first fell from the surface. Most of it is gone. What survives this far down is often just a fraction of the original clump, stripped of easy nutrients, picked over layer by layer through the zones above. Even so, that fraction still matters. For a waiting mouth in the dark, even a diminished flake is worth the wait. Certain deep-sea fish evolved eyes turned upward, tuned to catch the dim silhouette of falling particles. Species such as certain hatchetfish carry tube-shaped eyes pointed toward the surface rather than to the sides. This design gathers what little light exists from above. Every shadow might be food. Against the weak glow filtering down from far above, even a small falling flake casts a shape worth noticing. Bacteria coating a flake sometimes glow with a low light as it drifts downward. This glow may serve no purpose to the bacteria themselves, only a byproduct of their own chemistry. Even so, it turns an ordinary flake into a small drifting lantern. Nothing else marks its passage. In the black water of the midnight zone, that dim glow might be the only proof that something is still falling. An ember settles low in a hearth tonight, its glow fading by slow degrees, never quite going out. Let your breath match that same rhythm, in and then a long release, like light easing toward dark, without ever fully disappearing. Your shoulders can rest now, heavy against whatever holds them. Nothing here asks anything of you. Let your mind settle low and still, until sleep finds its own way in. Alone in total darkness, a dimly glowing flake can resemble a falling star. There is no sky here, no horizon, only black water in every direction. Yet the comparison holds. A tiny point of light moves downward at its own pace, briefly visible, then gone. Anyone, watching through a submersible window, might mistake it, just for a moment, for something falling from far above, rather than something sinking from within the sea itself. Sea cucumbers on the seafloor sense the arrival of settled particles from above. Dozens of them move in slow lines across the mud, feeling their way with short, blunt tentacles. They cannot see it fall, yet they seem to taste the moment fresh material settles nearby. Each one drifts toward the newest patches, drawn to wherever the last layer of snow has just arrived. Deposit feeders sift patiently through fallen debris for hidden nutrients. Worms, brittle stars, and small crustaceans comb through settled sediment, extracting whatever organic trace remains within it. Much of what they find has already passed through many other bodies before reaching them. Still, something usable is often left. This slow sifting recycles the last scraps of a journey that began far above, months or years earlier. A whale carcass occasionally interrupts the steady rain with sudden abundance. Where a body settles onto the seafloor, the usual thin trickle of falling snow gives way, briefly, to an enormous feast. Scavengers arrive within hours, drawn from the surrounding dark by scent alone. Nothing this size falls twice. Years of ordinary scarcity are answered, all at once, by a single overwhelming arrival. Researchers studying whale falls found scavenger communities persisting there for decades. Submersible teams returning to the same sunken carcass, years apart, discovered entire ecosystems built around it, worms, crabs, and bacteria, unlike anything found nearby. Certain species turned up only at Whale Falls, nowhere else in the surrounding sea. The carcass remained, in effect, a small oasis lasting long after the whale itself had gone. Mats of bacteria spread across fallen debris, working through what marine snow leaves behind. They break complex organic matter into simpler compounds that other creatures can use. This conversion takes weeks, sometimes longer, unfolding without any rush. Nutrients locked inside a single flake are released bit by bit, entering the food web long after the flake's original shape has dissolved. Almost nothing here goes to waste. Deep-sea corals grow in true darkness, far below any reef most divers will ever see. They cannot photosynthesize. Instead, they extend delicate arms called polyps, catching drifting particles as they pass. Each polyp gathers what little organic matter comes within reach. Some colonies here have grown for centuries, sustained almost entirely by this trickle from above. Their branching skeletons record years of steady feeding. Not everything falling through the water column began as living tissue. Tiny shells, spines, and skeletal fragments drift downward too, remnants of creatures that lived and died in the sunlit layers above. These harder pieces mix freely with the rest, sinking side by side within the same falling clumps. Some fragments are smaller than a grain of rice, yet each carries its own small record of a life once lived. Foraminifera are single-celled organisms smaller than a grain of sand, encased in shells built from calcium carbonate. When they die, their shells begin a fall that can stretch across months. Size makes gravity's pull almost imperceptible. Each one settles by fractions of an inch a day. Trillions sink every year, forming one of the ocean's most abundant, least noticed kinds of falling snow. Radiolarian skeletons, built from silica, take just as long to settle through dark water as their calcite counterparts. These organisms shape intricate lattices, resembling glass ornaments under a microscope. Once the creature inside has died, the skeleton begins a months-long fall. 2 shells, 2 sediments. Where they finally settle, each layer holds its own trace of the water that once surrounded it. Let your jaw loosen now, however it is resting. No need to hold it closed. Let it drift open by the smallest amount, the way a door settles when no one is pushing on it anymore. Your eyelids grow heavier with each breath, until keeping them raised feels like more effort than it's worth. Behind them, everything eases into a low, shifting dark, the kind that asks nothing of you. Let your eyes rest there, unfocused, sinking. Coccolithophores are among the smallest organisms in the ocean, single cells wrapped in microscopic plates called coccoliths. Each plate is built from calcium carbonate, shaped into a specific, almost engineered lattice. When the cell dies, these plates loosen and scatter into the surrounding water. Billions detach this way every day across the ocean's sunlit layer. Individually, each plate weighs almost nothing. Together, they form one of the most persistent kinds of falling snow. Pale coccolith plates drift apart from the flakes they once belonged to, settling now as countless individual specks. Alone, each is nearly invisible. Over centuries, they accumulate into thick layers of fine white sediment across wide stretches of open ocean floor. A single inch of that sediment can represent thousands of years, laid down one microscopic plate at a time. Dover's white cliffs rising along England's southern coast are made almost entirely of compressed coccolith plates. Each layer settled across the floor of a warm, shallow sea that once covered the region tens of millions of years ago. Nothing here fell quickly. Plate by plate, that accumulation pressed over time into solid chalk. Tourists photographing those bright cliffs today are looking, in effect, at a very long, very old snowfall, now solid rock. Aboard the research ship Challenger, naturalists spent the 1870s dredging samples from ocean depths no one had properly explored before. Many expected the deep sea to be a lifeless void beyond a certain point. Their nets told a different story. Organisms kept surfacing from the darkest, coldest water they sampled, again and again. The finding overturned a long-standing assumption and helped establish deep-sea biology as a serious field of study. Beyond the midnight zone lies the vast, flat expanse of the abyssal plain. It stretches for thousands of miles in every direction. Almost no light has ever touched it. The seafloor here is covered not in rock, but in a fine, pale ooze built from countless years of falling particles. Few landscapes on Earth are this uniform or this still. Here, the long fall of marine snow finally comes to rest. Every flake that survived the descent settles into a soft cushion of sediment. Layer joins layer, unnoticed. This is the ocean's true floor, built from what fell rather than what rose. It has taken the whole ocean above to make this ground. Sediment accumulates here more slowly than a fingernail grows. Scientists measure the rate in fractions of a millimeter each year. At that pace, Whole centuries pass, while barely a trace appears on the surface. Each layer forms so gradually that no single fall ever seems to matter. Yet together, they build entire plains of mud. 1 inch of seafloor mud can represent 1,000 years of falling snow. Everything settled within that thin layer. Every flake, shell, and grain arrived one at a time across an entire millennium. Compressed together, it looks like almost nothing. Held up to the light, it holds an immense stretch of time. A single inch in this place is a very long story. The abyssal plain remains one of the flattest, most silent landscapes on Earth. Its slope rarely changes by more than a few feet across many miles. No wind disturbs it, no waves reach this deep. Explorers comparing images from different plains often find them remarkably similar. Distance loses meaning where the ground looks the same in every direction. Sea spiders and brittle stars move slowly across the settled particles. Their thin legs barely disturb the surface as they pass. Some travel along currents so faint they are almost imperceptible. Each animal leaves only the lightest trace behind it. There is no hurry down here. Notice the breath moving through you now. Let each exhale stretch a little longer than the last. There is no need to guide it further than that. Shoulders loosen on their own. The next breath arrives without asking. The way tide returns to shore. Let it come and let it go, again and again, until counting no longer matters. Xenophyophores are single-celled organisms larger than a fist, though they consist of only one cell each. They build their bodies from mud, sand, and the remains of smaller creatures, cementing it all into a fragile shell. Some grow to the size of a dinner plate. Despite this scale, each one remains, biologically, a single living cell. They rank among the largest single-celled organisms known to exist. Manganese nodules grow layer by layer around a tiny original nucleus, sometimes no more than a shark's tooth or a fragment of shell. Minerals dissolved in seawater bond to that surface, one microscopic layer at a time. Across immense stretches of time, the nodule swells into a dark, potato-sized lump, scattered across the seafloor. Its growth never rushes. Researchers dating one such nodule found it had grown for several million years. Using radioactive decay as their clock, they measured its layers back through time. The nodule had rested in the same spot for longer than most mountain ranges have existed. It had outlasted entire ice ages. Somewhere on the seafloor, nodules like it are still forming today. Sediment cores drawn up from the seafloor, read like pages of a very long book. Researchers pull them straight out of the mud, intact, cylinder by cylinder. Each core preserves the order in which particles once settled. Nothing is shuffled. Held to the light, its bands look almost like handwriting, waiting to be read. Each layer within a core marks another era of falling snow, settled and compressed. Thousands of years may lie folded into a single band no wider than a finger. Older layers rest deeper, pressed thin by everything above them. Newer material stays loose near the top. The order never breaks. Time here moves only downward. Composition within these layers reveals traces of ancient climates. Grains of dust, pollen, and tiny shells all carry clues about the world they fell through. Chemists read isotopes locked inside these particles like a fingerprint. Some layers whisper of warmth, others speak of cold. The mud remembers what the surface has long forgotten. Colder eras left thicker, coarser bands within the falling record. Ice ages stirred stronger winds and rougher seas, carrying larger grains far out to open water. These heavier particles sank quickly, piling into dense, gritty layers. The seafloor still holds their weight. Even now, a geologist's fingers can feel the difference. Warmer eras left thinner bands, rich with older organic matter. Milder seas allowed only the finest particles to settle down, most of them recently living things. These delicate layers compress into narrow streaks, dark with carbon. Between one band and the next lies an entire shift in climate. The change rarely announces itself. A single core can hold a record spanning tens of thousands of years within just a few feet of mud. Compressed within, cold intervals and warm ones repeat like a long, slow rhythm. Each inch might represent centuries. A geologist reading one core essentially reads an entire Ice Age story, told in the plainest material imaginable. Hydrothermal vents occasionally interrupt this steady accumulation with mineral-rich plumes. Superheated water rises from cracks in the crust, carrying dissolved metals into the cold water above. As it cools, those minerals settle out, mixing briefly with the falling snow nearby. The plumes never last long. Afterward, the record grows strange, streaked with unfamiliar color, before the plain rhythm of falling resumes. Feel the weight of your body now, settling fully into the surface beneath you. Let your feet grow heavy first, sinking a little deeper with each breath. That heaviness moves upward, into calves, into knees, releasing as it climbs. Hips loosen. Your back rests fully into whatever holds it. Shoulders let go last, sinking their whole weight downward, as if gravity had finally been given permission to do its work. Falling snow near such vents mixes with particles rising up from below. Warm mineral water lifts fine sediment upward, even as ordinary snow continues its descent. The two streams pass each other in the dark. Neither pauses to notice the other. Nearby life often thrives on this brief collision of sources, drawing on both what falls and what rises at once. A team studying old sediment samples in the 2010s found something unexpected woven through them. The mud had settled decades earlier, undisturbed until it reached their instruments. Under magnification, fine fibers appeared where none should have been. The researchers paused. They checked their equipment, then checked it again. What they were seeing had not existed in the ocean before the middle of the last century. Microscopic plastic fibers turned up in mud that had settled decades earlier. The fibers were thinner than a strand of hair, buried in layers laid down long before synthetic fabric existed. None of that made sense. Yet there they were, having traveled downward the same way everything else does, caught inside falling flakes, arriving at a depth no one expected them to reach. Microplastics now fall alongside natural marine snow in many parts of the ocean. Tiny fragments cling to the same mucus webs that trap algae and dead cells, sinking together as one mixed cluster. Surface currents deliver plastic dust from far away. It arrives unseen. Once magnified, it settles into sediment beside material that has always belonged there, almost impossible to tell apart. The ocean's deepest trenches receive snow only after journeys lasting over an hour. Their floors sit thousands of meters below the already dim plain above, adding one more long stretch to an already lengthy fall. Even flakes that have descended for weeks face a final drop taking well over an hour on its own. Little survives that long. What lands has already given almost everything away. Within the Mariana Trench, sediment carries traces of the ocean's longest falls. Cores drawn from its floor hold particles that traveled farther than almost any others on the planet. Few falls travel farther. Some began as ordinary algae near a sunlit surface thousands of meters above, crossing nearly the entire height of the ocean before settling into this deepest record. Surrounding slopes often feed extra sediment into nearby trenches, deepening their store of fallen material. Loose material resting on steep walls above can slide downward during small disturbances, adding sudden pulses to the usual gradual supply. This makes trench floors thicker with sediment than open plains nearby. Sometimes the slope simply gives way. What collects here forms a record shaped by both steady fall and occasional slippage. Carbon carried within these falling particles can remain buried for thousands of years. Once folded into deep sediment, it sits far from the currents and life that might otherwise return it to open water. Nothing disturbs it there. Layer after layer settles above it, sealing it further from the surface world, holding it beyond the reach of the ordinary carbon cycle for a very long while. This burial slows how quickly carbon dioxide finds its way back to the sky. Left in open water or air, that same carbon might cycle through within decades. Buried instead, it can remain locked away for thousands of years. The difference matters. Each flake that stays buried removes, in its own small way, a trace of carbon from the cycle above. The biological pump plays a quiet, steady role in shaping the planet's climate. Each falling particle contributes only a small amount, easy to overlook against the size of the whole ocean. Multiplied across every basin, every season, every year, that modest contribution adds up to something the atmosphere can measure. It rarely draws attention. Earth's climate has depended, in part, on this pump working steadily long before anyone thought to study it. Somewhere beyond the room, a low hum rises and fades, like a house settling into itself. It might be a distant engine, or wind moving along an outer wall, or nothing you could ever quite name. No need to name it. Let it come, then let it go, and let your breath follow the same slow rise and fall, sinking a little further into stillness with each pass. Off Bermuda, a long-running measurement program tracked these falling particles for decades without pause. Instruments moored at a fixed station recorded whatever settled past them, month after month, without a single missed cycle. Its record grew into one of the longest continuous studies of ocean life anywhere in the world. Nothing dramatic ever happened, only years of careful repetition, one sample folding quietly into the next. That patient record helped reveal just how variable the fall can be from year to year. Some years brought heavy blooms and thick falls of snow. Other years passed with barely a trace drifting past the instruments. No two seasons matched exactly. Researchers studying the data found no simple pattern, only the slow rhythm of an ocean that never repeats itself quite the same way twice. Shifts in surface plankton can alter the falling supply for centuries afterward. A single change in which species bloom above can shift the chemistry of everything sinking below. Fewer diatoms might mean less silica reaching the deep. More soft algae might mean faster decay before anything arrives. Even distant changes at the surface leave slow, lingering marks on the sediment far beneath. Warmer oceans may change both how much snow forms and how far it travels. Rising temperatures can speed the growth of surface plankton, at least for a while. But warmer water also speeds decay, breaking flakes apart before they sink far. Less snow may reach the depths as oceans continue warming. The balance between these effects remains an open question among researchers studying ocean chemistry. This falling process is not unique to Earth's open ocean. Wherever a body of water holds life above and darkness below, something similar tends to happen. Particles rise, die, and drift downward in bodies of water far from any coastline. The pattern turns out to be less a peculiarity of the sea than a broader signature of standing water anywhere on the planet. Similar particle falls occur within very deep lakes, such as Siberia's Lake Baikal. Baikal reaches depths greater than most seas, holding a fifth of the world's unfrozen fresh water. Algae bloom near its surface each summer, then die and drift down through its cold, clear layers. The lake floor receives its own slow snowfall, far from any ocean, yet following much the same quiet rhythm. Fjords, cut off from open currents, host their own smaller version of this quiet fall. Steep rock walls trap water in place, letting particles settle with little disturbance from tides or waves. Sediment can build thick, undisturbed layers within a single fjord over just a few centuries. Norwegian and Chilean fjords have both yielded cores that read almost like miniature versions of the deep sea's own record. Researchers have wondered whether Europa's hidden ocean might host a similar process beneath its ice. Europa, one of Jupiter's moons, is thought to hold a saltwater sea sealed beneath miles of frozen crust. If anything lives within that hidden water, its remains might drift downward much as they do on Earth. No one yet knows whether such an ocean holds life at all, let alone falling snow. No spacecraft has yet confirmed what, if anything, falls through that distant frozen sea. Missions have measured Europa's ice shell and traced hints of its subsurface ocean from orbit. None have ever pierced that crust to look directly into the water below. Whatever process might exist there remains entirely theoretical. Earth remains, for now, the only place where this particular rain has actually been witnessed. In the 1950s, a team analyzing ancient seafloor cores first proposed reading climate history from falling sediment. Their samples, pulled up from ocean basins around the world, held layers stacked one atop another like pages. By studying the thickness and composition of each layer, they realized centuries of climate change had been recorded in the mud itself. The idea seemed unlikely to many at the time. It would later prove essential to understanding Earth's climate past. Feel a small warmth begin to gather at the center of your chest. Let it spread outward, gradual and even, down through your arms toward your fingertips. Now let it move lower, across your stomach, into your hips, and down through each leg toward your heels. Every place it touches loosens a little more, sinking deeper into the mattress. By the time it reaches your toes, your whole body may feel heavy and completely at rest. Their proposal, dismissed by many at first, grew into one of the foundations of modern climate science. The doubt did not last. Reading sediment layers as a record of the past became standard practice within a few decades. Ocean cores are now studied in laboratories worldwide, each layer checked against ice cores and tree rings. Marine snow, it turned out, had been writing history all along. Spring blooms across the surface send bursts of falling snow that arrive months later in the deep. Each spring, sunlight and nutrients trigger vast blooms of phytoplankton near the coast and open water. Within weeks, this abundance fades, and the remains begin their long descent. Nothing arrives quickly down here. By the time that surge reaches the seafloor, autumn or even winter may already have arrived above. Deep-sea creatures often feast on a season the surface has already forgotten. Depth stretches time into its own calendar, weeks or sometimes months behind the world above. The lag is real. Surface spring may already have faded into summer before its bounty ever reaches abyssal creatures. Seafloor dwellers effectively live within a delayed season, tasting last year's sunlight long after it has passed above. Time, in these depths, arrives through water before it arrives through memory. Every falling flake still carries a trace of sunlight, however faded it has become. Photosynthesis first captured that light near the surface, locking it into living cells. Light itself stays above, yet stored energy travels downward as those cells die and sink. Bacteria and animals in darkness draw a kind of borrowed daylight from every flake they consume. Even in total dark, life survives on something the sun once gave freely. Deep-sea metabolisms often slow to a crawl, stretching each rare meal across many days. Cold water and scarce food favor bodies that burn energy sparingly and move rarely. Waiting becomes a skill. Many deep-sea animals grow and digest far more gradually than their shallow water relatives ever do. A single meal can sustain some species for a week or longer without any trouble. A single meal eaten in the deep may have begun as sunlight months earlier. The food an anglerfish swallows tonight might trace back to a plankton bloom from the previous season. Between that bloom and this meal lies a long chain of sinking, grazing, and drifting matter. Nothing about the journey moves quickly. What began as light on open water ends, much later, as nourishment in total dark. Hundreds of millions of years have passed, with this fall continuing almost without interruption. Oceans have opened, closed, warmed, and frozen across that immense span, yet the descent of dead matter never truly paused. Nothing stopped it. Continents drifted into new shapes, while the pattern above them stayed essentially the same. Few processes on Earth have proven so persistent. The rain outlasted nearly everything else that has come and gone. Long before whales or fish ever existed, snow was already falling through early seas. Hundreds of millions of years before backbones or fins appeared, oceans already held drifting organic debris. No fish watched it fall. Early microbial life and small soft-bodied creatures shed remains that sank exactly as flakes do today. Fish, whales, and every reef arrived later, into a sea that had been falling long before them. Fossil hunters found traces of falling marine particles preserved in rock older than 500 million years. Layers of former seafloor, lifted into stone by shifting continents, still hold faint impressions of gathered organic debris. The imprint had survived. Researchers examining these formations recognized patterns matching the fall still happening today. The rock had, in effect, captured a single moment from an early ocean's rain. Their discovery showed that this steady rain predates almost every animal lineage alive today. Most branches of the animal family tree, from mollusks to vertebrates, arose long after this process had already begun. The rain came first. The fall did not evolve alongside life so much as life evolved within it, feeding on what already fell. Everything now swimming beneath the waves arrived, in a sense, as a guest. Let your shoulders sink into the mattress, heavy and slack. Picture an ember dimming in a hearth, its glow fading by degrees, never in a hurry. No task waits for you tonight. Each breath can be as small as that last curl of warmth leaving the coal. Let your mind rest there, in that fading orange light, needing nothing else. Older than most mountains still standing, the rain beneath the sea has never paused. Many peaks we admire today rose long after this fall had already begun, and will likely erode again before it stops. Mountains rise and fall away. This rain simply continues. It has outlasted entire ranges, watching them appear and vanish grain by grain. Every square meter of seafloor receives its own steady snowfall throughout each year. No patch of bottom mud goes without a share of this fall, from equatorial trenches to polar shelves. The amount varies by place. Some areas receive barely a dusting, others far more. Yet across the entire ocean floor, no square ever waits an entire year without something arriving. Gathered together, one year's fall could cover the entire ocean floor in a thin new layer. Spread evenly across every abyssal plain and trench, that layer would be thinner than a fingernail's edge. It would not be visible to any eye. Yet multiplied across millions of years, these thin annual layers built the mud that now cushions the deepest basins on Earth. The total material falling worldwide is measured in billions of tons each year. Marine scientists estimate the global total at somewhere between 5 and 12 billion tons of carbon annually, falling from every sunlit surface on Earth. The range stays wide because oceans differ so much region to region. Even the lower estimate describes a transfer of matter carried by life itself, larger than almost any other process on the planet. Nearly all of it was, however briefly, once alive. Plankton, larvae, tiny shells, and shed skins make up the overwhelming majority of what falls, each piece once part of something breathing or growing. Only a small fraction begins as dust or ash carried from land. The rain is less mineral than memory, built mostly from lives that ended in the sunlit water above. Every flake is built from things never meant to fall alone. A shred of algae might travel down, attached to a fish scale, a scrap of mucus, and the shell of something microscopic, all bound loosely together by chance. No single origin explains any one flake. Each is a small accident of togetherness, an assembly formed only because the ocean above rarely stays still. Some flakes measure barely a millimeter across. Others grow to several centimeters. Under a microscope, the smallest can look like flecks of dust caught in a beam of light. The largest, by contrast, resemble loose cotton, wide enough to see without any instrument at all from a slow-moving submersible. Size determines nearly everything about how a flake behaves once it begins its fall. An oceanographer once told colleagues the sight reminded her of the sea, remembering its own surface. Watching flakes glimmer past a submersible's window, she said it felt as though the ocean above had been folded down into the dark, piece by piece. Her colleagues found the image oddly fitting. Each flake, after all, still carried something of the sunlit world it had left behind. Larger flakes fall faster and arrive far sooner than their smaller companions. A dense, heavy aggregate can reach the deep seafloor within days, while a smaller, looser one may spend weeks sinking along the same path. Size alone can decide a flake's whole timeline. Two flakes leaving the surface together might arrive worlds apart in time, one long buried in mud before the other has even left the twilight zone. Slower flakes drift much like leaves settling through still autumn air, tumbling sideways before finding their path downward again. Nothing pulls them straight down in a hurry. A faint current can nudge one aside for hours, turning its fall into something closer to a slow spiral than a plunge. Watched long enough, even the smallest flake seems to hesitate, as if deciding again and again which way is truly down. There's a small give in the jaw when it finally lets go, a slackness spreading up through the cheeks and into the space behind the eyes. That space grows wide and unlit, room enough for thoughts to lose their edges. Eyelids grow heavy, heavier than they've felt all day. Nothing behind them needs shape right now. They can simply rest, unfocused, in that private dark, the way a room settles when the last light goes out. No two flakes carry quite the same mixture of origins. One might hold a fragment of algae bound to a scrap of skin. Another might carry only dust and a few broken shells. Chance decides which pieces settle out of the water together, and chance never repeats itself exactly. Each flake, in that sense, is a private history, unrepeatable, gone the moment it disperses into mud. The fall continues even through the fiercest storms and the darkest winter nights above. Surface waves may rise into towering swells, wind may howl across an empty sea, yet none of it reaches the layers below where snow keeps falling. Down there, the water stays undisturbed by whatever chaos plays out overhead. The rhythm below simply continues, indifferent to what the sky above decides to do. Anchored cameras have recorded years of nearly uninterrupted falling snow in the deep. Moored to the seafloor and left running for seasons at a stretch, these instruments captured frame after frame of particles sifting past the lens. Batteries were changed, memory cards swapped, and still the falling never seemed to end. Some of these recordings span more time than any single research voyage ever could. Watching that long footage, researchers notice the fall almost never fully pauses. Even during weeks when surface blooms seemed to fade entirely, faint particles kept passing through the camera's frame. The interruptions, when they came, lasted only hours, brief lulls swallowed almost immediately by the next wave of falling material. No true stillness ever showed up on the tape. This steadiness makes marine snow one of the planet's most dependable rhythms. Tides shift, seasons turn, and storms come and go, but this particular fall rarely misses a beat. Few natural processes on Earth run this continuously, this far from any human calendar. It simply keeps happening, year after year, whether or not anyone above is paying attention. The fall has continued through ice ages, warm eras, and long stretches of stillness in between. When glaciers stretched across half the planet, snow was still settling onto the seafloor below. When the oceans warmed and glaciers retreated, the fall adjusted its pace, but never truly stopped. Whatever the surface world was doing, the deep kept receiving its share. One retired marine biologist once remarked that this was the only rain she had watched never once stop. She had spent decades studying storms, droughts, and shifting seasons at the surface. But the fall she'd watched through submersible windows, she said, never paused for any of it. It was, in her words, the most patient weather she had ever known. This rain fell long before anyone stood on a shore and watched the sky for weather. It was already falling when the first eyes capable of seeing color opened underwater. It was falling long before there were shores at all, before continents had settled into their current shapes. Whatever forecasts exist somewhere in the deep, they've been running since long before forecasting itself was ever imagined. It falls without wind, without sound, without any witness most days. No storm troubles its descent this deep. No creature watches it land. Across most of the ocean floor, on most nights of the year, nothing living is present to mark the moment snow settles into mud. The fall asks for no audience and receives none. Satellites can trace the surface blooms that begin this fall, yet cannot see the snow itself descending. From orbit, a bloom appears as a smear of green or turquoise across dark water. That color marks where the fall will soon begin. But once the bloom fades and its cells begin sinking, the view from space goes empty. The descent itself stays hidden. It happens far below any camera in the sky. Notice your breath now, however it happens to move. There is no need to change it. Follow it down and follow it back up. Let each exhale run a little longer than the one before it, releasing a little more of the day. Let your shoulders drop. Let your jaw loosen. The breath keeps its own rhythm, older than any thought passing through you tonight. Rest inside that rhythm and let it carry you toward sleep. Life across the abyssal plain is thought to be thinner, pound for pound, than almost anywhere else on the planet. A square mile of that seafloor might hold less living tissue than a single suburban garden. Creatures spread thin, spaced far apart. Each one waits long stretches between meals. Yet even this sparse community depends entirely on what falls from above. Without the snow, there would be almost nothing left to sustain it. Distant surface storms eventually shape what settles far below, weeks or months later. A storm churns nutrients up from deeper water, feeding a burst of plankton once the surface calms again. That burst becomes fresh material, and eventually fresh snow. By the time it reaches bottom, the storm that caused it may be long forgotten above. The deep keeps its own clock. Nothing settling tonight began where it lands. Each particle started somewhere near the light. A flake resting on the seafloor once belonged to a cell near daylight, weeks or months earlier. It crossed the entire height of the ocean to arrive. Its origin was brighter. No matter how dark the resting place, the beginning was always closer to the sun. Every falling particle carries, in its own small way, the record of a life once lived. A shard of shell once housed something that grew and moved, and eventually died. A pellet once passed through the body of a creature feeding near the surface. None of it is inert. Even the smallest fragment holds a kind of biography, however brief, written before it ever began to fall. Seafloor sediment functions, in effect, like a library written in fallen snow. Each layer of mud is a page, laid down in its own particular year. Older pages rest beneath newer ones, exactly the way books rest on a shelf. Read in order, they describe centuries of blooms, storms, and stretches of stillness between. No page was written on purpose, yet together they hold a record few libraries could match. A retired ship's captain once described the sound of a sediment core breaking open as strikingly familiar. The crack of mud splitting along its layers to him sounded exactly like turning pages in an old book. He had spent decades aboard research vessels, listening to cores come apart on deck. The sound stayed with him. He said it was the closest he ever came to hearing the ocean read its own history aloud. Human bodies and ocean particles are built from many of the same ancient elements. Carbon sits inside a falling shell, just as it sits inside a beating heart. Calcium forms a diatom structure and a human bone with equal ease. The chemistry is shared. These elements were forged inside stars long before Earth ever existed. A person on any shore and a flake settling far below carry a history older than the planet itself. Carbon inside a falling flake and carbon inside a human breath may share a distant origin. Both trace back to the same stellar furnaces that forged every element heavier than hydrogen and helium. That carbon drifted through space for eons before finding its way into a young planet's crust and its oceans. Some of it built a diatom's fragile wall. Some of it entered a lung with tonight's next breath. No one can trace one atom's path, yet the possibility remains quietly astonishing. The rain beneath the sea will keep falling long after this night has passed. It will still be falling when tomorrow's light touches the surface. It will still be falling long after every listener tonight has grown old. Plankton will bloom and fade. Sediment will thicken by another sliver. Cores will lengthen year upon year. The pace does not hurry, and it does not stop, whether anyone is watching or not. That steadiness is its own kind of comfort. Somewhere below the waves right now, another flake is drifting into the dark. It has no name, no witness, and no need for either. It is only on its way down, exactly as countless others have gone before it. That may be enough of an image to carry into sleep tonight. Something small, falling without hurry, always arriving somewhere. Rest now, the way the deep sea rests, unhurried and dark. Sleep well. Good night.